Don Cadet, and I am enrolled in Section 2 of Organic Chemistry Lab with Mr. Paul. So today we'll be talking about ester. And we're getting this ester through a means of Fischer esterification. There's many ways of forming an ester, but that is the way that we'll be talking about today. So we have our ester being propyl hexanoate, and also known as propyl carproate, and we have the molecular formula on the left being C9. We have 9 carbons, 18 hydrogens, and 2 oxygens, and on the right we have the bond line structure. So we're seeing that we have propanol reacting with our acid, hexanoic acid, and we have our sulfuric acid that is in the reaction that is forming our ester as well as our byproduct of water. Now, this sulfuric acid is not doing anything thermodynamic wise, but the kinetics is actually doing a lot because it's causing the reaction to be a little faster. So that's really what it's doing, but thermodynamically speaking, it's not doing anything. So just to look at the propanol, we see that it's in excess, and the reason is because we're actually using it to protonate the oxygen on the carbonyl group, and we're seeing how it can be used as a solvent as well as a nucleophile in this reaction. So we're seeing how the first step is actually the protonation of this carbonyl group oxygen by the sulfuric acid, and of course we end up getting our sulfuric acid back because it is catalyzed. So in the end, we get our reactants being our propanol, our alcohol, our acid, as well as, of course, the acid catalyzed, and our ester and water being formed under Fischer esterification. So that's really the reaction mechanism side of it. So let's actually move forward onto actually talking about the theoretical yield calculations. So the theoretical yield calculations, we have a propyl hexanoate. We have to talk about our unknown alcohol, propanol, and so we have a 0.015 moles, and we're multiplying that by the density, and we're getting the milliliters used, or just the amount used, both in milliliters and grams, of course. So we have our propylic acid being 0.015 moles, and we're multiplying that by 2 because of the twofold comparing to alcohol. So we're doing this to get the limiting reagent, because we need to get that number to actually get the grams formed of propyl hexanoate. So when we actually do this, we actually end up getting 2.3736 grams formed, because 158 is the molecular weight of our propyl hexanoate, or ester. So that's really the theoretical yield calculations. Let's move on into really let's see, the setting up of the reaction. So there's actually several steps of this reaction. So we have to prepare several stuff. The glassware setup. We have to transfer some the calcium chloride for the drying tube. We have to remove the calcium drying tube. We have to cap the reflux condenser. Just several things that we have to do in this reaction. But just looking at calcium, or calcium chloride, the intended use of this is actually used as a drying agent of the water that is formed by from the sulfuric acid. So we're actually seeing this playing a factor in this reaction. So moving on into the product isolation, we're seeing there is an extraction step, of course, and we're adding sodium bicarbonate. Now, this sodium bicarbonate is to neutralize the hexanoic acid and sulfuric acid on top of the organic layer. So in the end, we are collecting ester in a microcentrifuge tube, but we're capping the tube, of course, and we're placing this in our drawer at the end. So moving on to the product purification step, we're using Pasteur pipettes to transfer crude ester into a vial. So we're distilling this to further our reaction. So this ester distillate will collect into a Kohler Hickman still, right? So, and after this distillation transfer, the ester into using Pasteur pipettes to a clean and tailored vial. So really, there is anhydrous sodium sulfate, and that is really just to remove excess water from the layer solution. So it's basically acting as a dry agent, right? So moving on to our physiochemical properties of ester, we have our CAS number here, 626777. That is really the identification number, and we have the molecular weight of our ester being 158.24. And then we have our boiling point, of course, 107 centigrade, 187 centigrade to be exact, and our melting point being negative 68.7 centigrade, and our density being 0.86 or 0.9. So we do end up getting this, and the appearance of our ester is really a colorless, clear liquid. So we'll talk a little bit more about the appearance or the properties of this later on in this video. So let's move on to the H and Mars, or just the spectrums in general. So first, let's talk about propanol. So we have 4 signals, right? We have A, B, C, and D, right? We have our OH being observed a chemical shift ppm of 2.26. And then we have our CH2 being the most downshield at 3.582. So and then we have our peak multiplicity and being a singlet, a triplet, a multiplet, and we're using the n+1 rule in these cases. So we have our chemical shift literature values, but really the things that we focus on is really the atom groups and seeing what kind of peaks that it is forming, is being categorized, and where it is being. So moving on to the CNMR, so we have our C, B, and A. We have 3 signals, and just because there's 3 carbons, right? When we're seeing this atom group right here, we have CH2, CH2, CH3, and the observed chemical shifts being 60-ish, 20-ish, and 10. So this 64 one is actually the most downfield one. That's because it's right next to the oxygen, right? And this has to do with being electronegative and the dipole moment that goes into play here. So we have our HMR for propyl hexanoate. This one having several signals. And the most downfield is actually 4.02 or 4.03. And this one is CH2 that is categorized at A right here, right? And that's right. That's because it's right next to the oxygen, right? And the carbonyl group. That's why it's so downfield. And this one is being a triplet because of the 2+1 rule, right? Because of 2+1, so it's causing 3. This is a triplet, right? So we have in our peak multiplicity of triplet, multiplet, quintet. There's several types here, and then we just have to categorize all of them. So let's move forward into the CNMR, C13, propyl hexanoate. So right here we have our carbon double bond O group being the most downfield, and we have our CH2 to several CH2s and 2 CH3s, one at each end right here. So we are able to observe the chemical shifts using the database that we were given, and we're seeing the chemical shift values in the literature ppms, right? So we actually have in total of 1, 2, 3, 4, 5, 6, 7, 8, 9 signals, right? Because there's 9 carbons, right? When we're talking about propyl hexanoic in the beginning, remember when I said there was 9 carbons, right? When we were looking at the molecular formula. Let's move on to HMR of a propanoic acid. So we're seeing that there's 3 signals here. That's really because there's 3 hydrogen groups. There's one here, 2 here actually, but they're seeing the same things, and 3 here, seeing the same environment. So we're having observed chemical shifts at 11, 2, and 1, and the one at 11 is a singlet, and that's because there's nothing next to it, right? So it's 0 plus 1 plus 1, so we're getting 1, right? So this is being a singlet, and we have a quartet and a triplet. And you're able to see the signals and the chemical shift literature values. So let's move on to C13, NMR propanoic acid. So we're seeing this here. We have A, B, and C. So we have CH3, CH2, and C double bond O. and the C110 is the most downfield, sitting at 181.46, and that's because it's right next to this oxygen and this oxygen, right? That's why it's so downfield. So an interesting fact about our product while we're going through it is just the appearance of it all, just being a clear liquid. We're actually able to see this, or not see, but know the smell of our ester, and it's actually used as a flavor ingredient, and it's found in apples, grapes. It has the properties that it has allows it to be used in several or various alcoholic beverages, but it has a more of a tropical, fruity scent to it. So it has several uses. The appearance of it being a clear liquid. So we're seeing this in this is one of the interesting facts about our product. So yes, thank you so much for watching this. This was a video covering the Fisher esterification of our propyl hexanoate. Thank you.